The afternoon session of the first day, and it's a pleasure to me to introduce you Reina. She comes from France, El Penaché, and she will talk about the beauty of the Higgs boson. So enjoy Reina's presentation.
Hi, can you hear me? All good? Perfect. Okay, excellent. Well, thanks a lot for the invitation, and thanks a lot for coming and listening to this presentation. In this presentation, basically the main actor will be the Higgs boson, and the stage or the context will be the center of the Atlas detector at the Large Hadron Collider at CERN. I will try to touch on the following topics. First, do like a historical review of how did we arrive to the Higgs discovery in 2012, and what has happened since then. In the last 11 years, how much have we improved our knowledge, our understanding of the Higgs particle? I will focus on the relationship of the Higgs with fermions, and in particular with the B quarks or the beauty quark, and hence the title of my presentation, The Beauty of the Higgs boson. I chose that particular relationship with the bottom quark, the beauty quark, because I want to give an example of how we go from discovering a particle to doing now precision measurements and using this particle as a tool for discovery of new physics. Not only the understanding of the current theory, but going one step ahead and in the discovery of new physics. So, how well do we know the Standard Model? This is a very complicated one, but if you go and see the teacher of, you can go and see the teacher and you can see the very nice and very simplified equation for the Lagrangian of the Standard Model. It's a very elegant one. We have this particular piece of the Standard Model that is that describes the forces, 3 of the 4 forces that we know. The second part describes how the forces act on matter. The third one, how the particles obtain their mass, and the last one, how does the Higgs boson actually works. And this particular theory, even though we know that it's not describing everything we know in the universe, we must accept, and we must accept at this point that it's a huge success in terms of the experimental point of view. It predicts the particle content, and also the particle interactions, at the point that even the last missing piece of this particle was found in 2012, the Bro-Engler-Higgs boson. So in terms of the particle interactions of the Standard Model, the interactions between the leptons and the bosons, photons, W bosons, Z bosons, has been well understood already, even from previous accelerators. The triple couplings, WW with Ws and Z, have been observed at the LEP collider accelerators and also at the LHC. We managed to find the Higgs boson and to prove the couplings to the fermions and the vector bosons in the LHC. The quartic vector boson couplings, the ones that we have here, they are not observed yet. They are starting to be accessible just now. And finally, one very important piece, which is the Higgs-F coupling related with the di-Higgs production, is also one open point. So even though we can say that the Standard Model is a huge success from the experimental point of view, we can also say that we still have a few things to test in the Standard Model, and there is still room for new physics and for physics beyond this nice theory that we have. So what was the road for discovery? How did we arrive to that point in 2012? So this will be a very simplified summary, a summary of the work of many people working on the detectors, working on the analysis. The LHC was approved by CERN, by the CERN Council in '94, and the civil engineering work starting in '97, the commissioning starting in 2008, And it was at that point that we have an unfortunately accident with the superconducting dipoles when we were running the first beam. So actually the starting of the data taking was delayed a bit. We finally had useful beams for physics analysis in 2010 after a year and a half of intensive work by the people at CERN in order to fix this. And very, very quickly, the two experiments, Atlas and CMS, started to analyze the data and to exclude actually the existence of the standard model Higgs in a very large mass range that was spanning almost up to 600 GeV, except for a very, very narrow window around 125 GeV. So this morning, we hear in the presentation from Professor Ellis why it was so important, the fact that it was discovered at this mass, 125. In that particular point, we have access to different channels and production modes, which allow us actually to deepen the understanding that we have of the electroweak symmetry breaking mechanism. And it was finally in 2012 that we could claim the discovery in a very independent way between the Atlas and the CMS experiment, which is very important to have two independent experiments in order to claim a discovery as important as this one. Okay, so how do we produce actually the Higgs boson at the LHC? At the LHC, we have four main production modes. The first one, and the one that has the highest cross-section, is the gluon-gluon fusion. Is the one that you have here is the main production mode. It also have a lot of large backgrounds, so it's a very, let's say, challenging production mode when we are analyzing the Higgs boson. The next one, in terms of production, is the vector boson fusion, or VBF for short. In this particular case, we produce the Higgs together with two quarks that in our experiments, in our detector, it will produce a shower of particles, or we also call or reconstruct this shower of particles as an object that we call a jet. So it's a very clear signature in the sense that we have the Higgs boson and two jets also in the final state. Is important for triggering and background rejection. The next one is the associated production of the Higgs. So we produce the Higgs, but it's produced together with a W or a Z boson in the final state. And this is very useful for the accessibility to the gauge coupling. And finally, the production with two top quarks in the final state. And this gives us the access to the top Yukawa coupling. But this is not the whole story. We need to produce it, but we also know that the Higgs is a very ephemeral particle. It is produced and it decays almost instantly, okay? So we need to take care of the production, but we also need to take care of the final decay topology of the Higgs boson, because at the end, in the detector, we are not going to see just the Higgs going around. We will see the products of a decay. And actually, most of the time, the largest decay that we have of the Higgs boson is the Higgs 2BB. The dominant decay is 58% of the time. Then we have the WW with a 22% production mode. We have ZZ, a bit smaller, Tau Tau as well, Gamma Gamma, and then here we have like a bunch of small cross-section decay channels that are being studied right now as well. And then we might say, well, great. I mean, if you have 58% of the time a Higgs decaying to the beauty quark, that's the channel that you need to go for, right? I mean, this is the one that you will see the most. Unfortunately, the decay channel and the cross-section of the decay is not, or the branching ratio, sorry, is not the whole story. We need to find the balance when we are doing an analysis, an interplay between the production and the decay channel that you have of the Higgs. Why? Because this particular channel is true, it's the largest branching ratio, but it also has the largest backgrounds coming from multi-jet, coming from QCD, quantum chromodynamics. And the orders of magnitudes of the cross-section of QCD is much, much larger than the signal of the Higgs. So it's a very, very challenging one. This is actually why this was not actually the signal or the channel that we used for discovery. Surprisingly, it was Z, WW, and the two photon decay channels, the one that were used for the discovery, which is very surprising, right? Even if you see the branching ratio for the gamma-gamma is super small, but it's a very clean channel in terms of background, and also the two detectors have excellent calorimeters that allow us to reconstruct these particles. So these were the channels that we used for the discovery. They were the first ones to be observed. It's been already 11 years of data taking, 11 years of improving the performance and the analysis methodologies, 11 years of improvement the understanding, improving the detector, but also improving the understanding of the detectors that we have. 11 years where we actually have been able to collect 15 times more data than what we had at the beginning, at the moment of the discovery. And this has allowed us to do many things. There has been many breakthroughs in the last 11 years. For example, the observation of the Higgs to tau-tau decay channel. This happened in 2016. The beauty channel Higgs to BB, Higgs to 2B quarks, was finally observed in 2018. The observation of the TTH production mode, combining the different decay modes, was also observed. We have evidence, 3 sigma evidence for channels very small, with very small branching ratios, like mu, and also the Z gamma decay of the Higgs. And there are several still ongoing searches, and this is why this question at the beginning of the talk, like, how well do we actually know the Higgs, the standard model? How well have we been able to prove and to test all the predictions? So there are still in the Higgs sector some channels that we have not observed, and we are still searching for them. CC, so the decay to 2 charm quarks, mu, and also the Higgs production mode that is completely related with the shape of the Higgs potential and the understanding of the Higgs potential. And here is an example of all the precision measurements that we are doing with the first decay channels that we discovered. For example, here you have the PTX spectra of the Higgs decaying to, or the Higgs candidates decaying to 2 photons and to 4 leptons. Other impressive precision measurements is the fact that, for example, we know now the Higgs mass with a precision of 0.1%, something that it was very far from that at the beginning in 2012. So let's take the example of the beauty Higgs, the Higgs decaying to BB, and let's go through the process of being discovered in 2018 to being a channel right now that allow us to test really high transfer momentum of the Higgs, and also allow us to use very new techniques within the collaboration within the detector. So why studying the Higgs to BB? We already say it. It has the largest branching ratio, and it controls the Higgs total width, and therefore branching ratio of all the other decays. It's a direct proof of the Yukawa big quark coupling, but more importantly, it has high sensitivity to new physics when we are in the high PT regime, and I will come back to this just in a moment. This is completely related what we were discussing at the beginning in the morning regarding the EFT theories. Again, there are different analyses that are performed by Atlas and CMS depending on the Higgs production mode. The different modes has been tested so far. I will focus on this particular one, the BH, or the associated production of the Higgs with a W or a Z, just because it's a very interesting one in order to test new techniques of reconstruction, new techniques in the detector site, and is the most sensitive mode for Higgs to BB. So how do we explore actually the beauty of the Higgs in this channel? Well, we need to reconstruct the vector bosons, and we need to reconstruct the Higgs going to BB. We need actually from all the particles and all the puzzle pieces that we have in the detector, we need to go back in history and trying to reconstruct what is coming from what is coming from the vector boson, what is coming from the Higgs. And we compare with the standard model predictions. We can have the W decaying to leptons, neutrinos, or decaying hadronically to two quarks, the set decays to leptons, and in this case the Higgs going to BB. This channel, we mentioned already, is great. It has the largest branching ratio, but it also has a lot of challenges from the experimental point of view. We have a poor kinematic resolution. We have the highest background rates, and sometimes those are backgrounds that are not well modeled by simulations. And it requires an excellent performance from our calorimeters and from our inner detectors in order to be able to identify what is a jet coming from a big quark in particular. And we will focus on the high transfer momentum because this is a particular section or a particular regime where that is sensitive to new physics beyond the standard model. So when we are talking about new physics, we can look for it in two different ways. One that we call direct. Basically, we are looking for resonances, new peaks, new particles. The second one, which is very interesting, is the indirect search. So what if the particles predicted by new theories we cannot produce them at the energies of the LHC? What if the mass is beyond the reach of the energies of the LHC? But we cannot see the effects of the tails of those kind of distributions. This is what we call indirect search, the deviations in the distribution tails. Current indirect searches in Atlas, and also the case in CMS, are mostly independent of theoretical models, and they use effective field theories in order to try to parameterize possible tails or possible discrepancies between the predictions of a standard model and the data in the tails of distributions. The deviation from the standard models are parameterized by adding higher order operators in the standard model field. So we have the Lagrangians of the standard model, and we add additional operators, additional terms, in order to parameterize the effect of these new interactions or the effect of maybe these new particles. And that means that if we search for a standard model deviation in EFT, we have a very high sensitivity when we are going to the tails, when we are going to the high PT regimes of this kind of searches. This is why we will be focusing on the high transfer momentums in the analysis that I will be presenting. However, in order to do this, in order to be able to access that regime, we cannot use just the normal techniques and the normal way of reconstructing particles in our detectors. We need to use new ones. In the last few years, the reconstruction, the developing of taggers or algorithms in order to identify bosons like the Higgs, like the W, like the Z at high PT has been a very active field, not only from the experimental point of view, but also from the theoretical point of view. When we are in a high PT regime, what happens is that the decay products, the hadronic decay products, they cannot be reconstructed in an independent and like in an individual way, because there is a high Lorentz boost that is introduced, and then the decay products, they become very, very close. So you cannot just reconstruct them individually, you need to reconstruct them together in a new way. And in order to do that, what we do is that instead of reconstructing them in this way, using small radius jets, we try to use like large cones of jets in order to reconstruct them. What is very interesting is that the energy deposition inside those objects are completely different if the jet is coming from a quark or a gluon, which is mostly the background that we have, or if it's coming from a W or a Z or a Higgs. The energy deposition is completely different. You have two core of energy instead of one. And there are many techniques that we can develop in order to tag whether the jet is coming from a Higgs, whether it's coming from a W, whether it's coming from a Z boson, or if it's coming from quantum chromodynamics, like just a quark or a single gluon. So I will not going to enter into details. I'm sure that you have heard a lot about Atlas in general, but we will be discussing an analysis using a data set that was collected by the Atlas experiment with great capabilities in terms of verticing tracking, muon detection, and also calorimeter. The data set was collected between 2015 and 2018. We will be using that full statistic. And I will be describing two main analyses. The first one is a Higgs that is producing with a Z or a W. The Higgs is the beauty Higgs, and the Z and the W are decaying electronically. So the Z going to LL, or neutrinos, and the W is decaying to electron and a neutrino, okay? So in this case, we basically can have three main channels. A zero electron channel, the Z is going to neutrinos, a one electron channel where the W is going to an electron neutrino or a muon neutrino, and two electrons where the Z is going to two electrons or two muons. The Higgs boson candidate is reconstructed, as we mentioned, with a large radius jet in order to capture the whole decay in a single object, and we tag this object as coming from a Higgs. And we compare with the theory. This comparison is done in several ways. We can compare kinematic variables with the simulation. We can measure the cross sections and measure, which is basically the probability that a specific process will take place. We can also have theoretical calculations that provide us with different effective cross sections and compare these with effective field theory predictions. This is one distribution. In this case is the PT of the Z boson. So here we can see how the data agree with the standard model prediction. There are several categories in the analysis that goes in terms of the number of leptons, the PT beams that we have, so the beams of transfer momentum. So at the end we have like 10 signal regions, and we have also control regions in order to control the backgrounds that we have in this particular analysis. The main backgrounds are coming from W or Z plus jets and the top production. And there is a measurement of the BZ plus process with Z2BB to validate this particular strategy. And here we have one of the first results for this analysis. We have the cross-section measurement in two different transfer momentum regions. We can already start to see that we are reaching and we are able to measure the cross-section in a quite high transfer momentum. We have a beam that goes in a transfer momentum between 250 and 400, and another one that goes beyond 400. There is a high compatibility with the standard model prediction as well, and we have a particular significance here of this process of 2.1. But just remember that we are focusing on the high PT, in the high transfer momentum. When we combine with the low transfer momentum, we have more than 5 sigma, of course. So how do we interpret this in terms of an EFT? These cross sections that we saw here, we can actually use this model, these cross-section measurements, in order to constrain the parametrizations of the EFT for some of the operators that are added to the Lagrangian of the standard model. If the coefficients that we have here that accompany the parameters, if they are close to 0, that means that we have something that is very standard model-like, that is super compatible with the standard model. What we are looking for is whether or not, if we are looking at this distribution and these processes in the high transfer momentum, whether or not we have deviations in that case, and whether or not we have values of these coefficients that are called Wilson coefficients that are far from 0. When we do that, in the particular case of the beauty Higgs, the Higgs decaying to BB, what we can see is that within the errors, within the uncertainties that we have, everything is compatible with 0. Another way of looking into this is, what if the vector boson, the W or the Z, is not decaying electronically, but it also decays hadronically to 2 quarks? And this is what we call the boosted hadronic WH or ZH. This is the first dedicated search for the production of BH associated production in the full final hadronic final state. This particular analysis, basically you have two large jets that are back to back, and one of the jets is tagged as coming from a Z or a W, and the other one coming from a Higgs 2BB, using a deep neural network for this. The main experimental challenges are the flavor tagging, the background modeling, and the resolution in this case. This is an analysis that is completely dominated by QCD, and one of the main challenges is how to model the QCD background, because we don't use simulation. It doesn't behave completely well in all the different phase space, so we use data-driven in order to fully control the multi-jet background in this case, and we have some control regions and validation region in order to validate this. These are some of the distributions, in this case of the Higgs max candidate. And one thing that is extremely impressive is that now, with this kind of analysis, we are reaching even higher transfer momentum. Basically, we are having data that can reach or be very close to the TeV scale, starting to be at reach. We have three different transfer momentum, one from 250, 450, 450, 650, and greater than 650. And this is the region that is extremely important, again, to look for new physics and to test the EFT's interpretation. So I show the latest results in the case of the Higgs beauty. But as I mentioned, the Higgs physics in general has made extremely good improvements in the last 11 years. CMS and Atlas, they made a lot of progress in understanding this sector, with analysis that has an increasing complexity. An increasing complexity in terms of how the analysis is defined, how the statistical model is defined, the analysis definition as well. And here you can, last year actually, during the 10 years anniversary, both experiments, they put together a very comprehensive summary of what we knew about that particle. Here you can see a very nice summary of how the signal strength for the different decays, the different production mode and the different decays behave. We can see that so far everything is very standard model-like. We can also see the terms of the coupling as a function of the mass, and this is very impressive to see how well actually the linear dependence between the couplings and the mass is, in particular if you consider that there are several orders of magnitudes here. And again, there are several things that we're still searching for. The Higgs 2 mu, the Higgs 2 CC, the charm quartz, and also the di-Higgs production. This in particular, the di-Higgs production, help us to test the shape of the Higgs potential. It's a very difficult process. Basically, it's a very rare process in the sense that the cross-section is basically 0.1% of the cross-section of just producing a single Higgs. It's a challenge, but it's one of the challenges that we will be looking forward to tackle in RON 3 and also in the high luminosity LHC. So what we know right now is our data is telling us that we have a scalar particle with a spin 0 and even parity. It has this mass. It's very standard model-like so far, but we still need to test a few things of this particle. And more than that, we know that the standard model doesn't accommodate everything we know about the universe, right? This morning, we heard about several theories where the Higgs, or we heard about several new physics theories where the Higgs played a key role. So there must be something else. And maybe the Higgs is a tool that will help us to unlock these mysteries. So I will just leave it here and just be open for questions. Thank you.
Thank you, Reina, for this